Good morning. Assalamualaikum. Before we start, test should be next week, right? 28 during class hour. But DEXA is not available during class hour. Can we make it earlier for the test? To be 11 to 12:30. Do you have any class before that? Ibrahim, do you have class? No class. Okay, so we will bring forward from 11 to 12:30 in DEXA. Okay, topics covered here, CLO3. Chapter 3 means I can say all chapter 3 is related. Okay, because in adiabatic flame temperature, you still need the first law analysis. In water gas shift reaction, you still need this first law analysis. So all related. Chapter 5, which relate to CLO4, will cover on the sustainable fuels. Okay, another thing is related to the class, group assignment. Today is the last date to form a group. So far, these are the groups. Group 1 already full. Okay, I have logged the sheet. Group 2 still have 2 space left. Group 3, only 3. Group 4 and group 5 still empty. So this group 2, Abdul Karim and Ibrahim, I will move you to group 2. Okay, group 4, I'll move to group 3. Okay, so please find the group members and discuss together. So this sheet is complete. So I protect the sheet. Remaining group 3, 4, and 5. Okay, please remind your friend, for those who haven't formed any group, to do it by today. Okay. Okay, we are done with chapter 5 last week. So today I will proceed with chapter 6, environmental analysis of combustion process. This is our last topic. If enough time, we can finish by today. If not, we will continue on next week. Okay, basically, there are some repetitive topics. So I will go through a bit faster for those, just for discussion. Okay, basically chapter 6, you will go through environmental analysis of combustion process. So that means in combustion, what from the flue gases released, so you should analyze whether the concentration of the flue gases is affecting the environment or not, and how to analyze them. What are the formulas to use and what are the standards to follow? Okay, so by the end of the chapter, you will know what is the major pollutants and the quantification of emission. We have emission index, we have emission factor, Okay, and we have few other formulas. Now, major pollutants from combustion system, as we have gone through all 5 topics, we commonly came across on the flue gases, which consist of CO2, CO, what else? In the flue gases, what you have? H2O, N2, O2. That one is common, right? But in real combustion, there might be some particulate matter. So particulate matter is a fine particles. Usually, it will the DOE classify as particulate matter within their specific range. For example, PM10. PM10 means the particulate matter is 10 micron. Okay, PM 2.5. So the particle is 2.5 micron. Okay, I will update this updated slide in CN. If you notice, during the haze season, they will come up with all the API, the air pollution index, the particles, PM10, PM 2.5. So you should know the meaning of each abbreviation. Okay, basically the particulate matter, as we know, came from the vehicles with occur from the combustion engine, okay, power plants and various industrial process. The haze itself comes from combustion that occurs elsewhere, open combustion, okay, open fire burning. So we also have sulfur oxides in the flue gases. It can be in SO2, SO3. Okay, various industrial processes are the source for sulfur oxide. If the fuel contains S, sulfur, so you will have sulfur oxide in your flue gases. Because some petroleum and coal often contain sulfur compounds. So that's how the sulfur oxide produced in the flue gases. From the SO2, it will form H2SO4, okay, with the presence of NO2 catalyst. Then that's how the acid rain comes. Okay. So those acid rain have its own environmental impact. Now NOx, these are released into the atmosphere when industrial combustion occurs at high temperature. Okay, NOx. NO2, that one is we can say safe NO2. So, but other NOx, nitrate, okay, nitrate can form nitric acid. Okay, then carbon monoxide also can be detected in the flue gases, where carbon monoxide, CO, it is a flammable gas, okay, odorless, and it has its own environmental impact. This is due to incomplete combustion. Okay, and it can be toxic even at low concentration. Okay, so that's why in certain process they will convert the CO to CO2. For example, the water gas shift reaction. Okay, the CO2 converted to the CO converted to CO2. Okay, other than that, we also have unburned and partially burned hydrocarbons. So it is incomplete combustion, whereas in industry, there is no 100% complete combustion. Okay, might be 90% complete combustion only. So the rest of it will be unburned or partially burned hydrocarbon. Okay, the VOC, volatile organic content, and then the methane. Okay, greenhouse gases. Okay, it can affect to the greenhouse gases in creating ozone, the O3. Okay, too much ozone is not good as well. For the VOC, we also identify the aromatic compounds. Okay, some of the aromatic compounds, it can be carcinogenic, okay, and may lead to health issue. Not limited to leukemia, but other health issue as well. Okay, that's why your flue gases should be treated. Okay, the flue gases in the industry should be treated. How to treat? Later we go through. Okay, in the flue gases also, some of it can contains the polycyclic aromatic hydrocarbons. The simplest is the naphtha. Okay, naphtha, this is the structure of the naphtha. Two benzene ring. Naphtha occur in combustion products of some petroleum derives. Okay, include anthracene, phenanthrene, pyrene, etc. So naphtha, the application, example of naphtha is the mothball. The mothball comes from naphthalene. Okay, it's the product of naphthalene. So this naphtha comes from PAH. Okay, polycyclic aromatic hydrocarbons. The source, of course, the propyl petroleum. Okay, so this part have serious effect on health. And attention has to be given to their formation even in trace amount. So even though in low concentration, it can affect the health. Okay, so now we have particulate matter, the PM. I conclude now. PM, sulfur oxide, SOx. Those are the major pollutants. PM, SOx, NOx, CO, the unburned hydrocarbons, and also the PAH. Okay, so those are the major pollutants in the combustion products. Now, how to control it? If let's say you detect CO, your CO is exceeding the standard, and perhaps you have SOx in your flue gas. So these are, and we will discuss three methods, okay? But there are various methods in the industry. Basically, the fundamental of it is the scrubber, the use of scrubber. There are a few types of scrubber. I will explain three types of scrubber. Dry scrubbers. Okay, basically dry scrubbers is the dry adsorption scrubber. It injects dry gases. Okay, no application of the mist, the water, liquid, anything. Okay, it has neutralizing chemical agents, which cause the gases pollutants undergo a chemical reaction which either neutralize the pollutants or convert them into inertial substance, less hazardous substance. Okay, the dry scrubber. Later I share with you the diagram. So dry scrubber, it use chemical agents to neutralize the pollutants. Once the chemical reaction concludes, filters within the scrubber chamber collect and remove the spent agents, okay, from the clean gas emission. In some cases, the collected agents here refers to the chemical agents, can be washed and reused for future scrubbing process. Otherwise, need to be disposed. Okay, typically, dry scrubbers are used to remove or counteract acid gas within industrial emission. Okay, acid gas. So acid gas, that's why in the first point over here, chemical agents, sodium bicarbonate, the salt, to neutralize the acid. Okay, so it will reduce and neutralize the acidity of the emissions. That one is dry scrubber. Now wet scrubber, as you all know and familiar, it use water, liquid. Okay, wet adsorption scrubber or wet collectors typically use the water to collect and remove water soluble gas and particulate pollutants. Okay, the wet scrubbing process either passes a gas stream through a liquid solution. Okay, gas pass through a liquid solution or injects a liquid solution into gas stream. Okay, this one, the sprinkler, the use of sprinkler. As the gas stream comes into contact with the liquid, the solution will absorb the pollutant. Okay, so the typical wet scrubbing equipment, we have the venturi, pipe bag, and bubbling scrubbers. Okay, but this one, inject a liquid solution into a gas stream. This one is the usage of the sprinkler. You have gas coming in. Then on top here, you have sprinkler, spray the water. So the water mist. The water will absorb the pollutants. Then down here, you have water plus the pollutants. Then up here, you have a clean gas coming out. Okay, another one is electrostatic precipitators. This one, it uses electrical forces. They use electrical forces to move particles from the air stream to collection plates. Okay, the particle passing through the precipitator, particle here refers to the flue gas. Okay, the raw flue gas pass through the precipitator and it's given a negative charge by force. Okay, once it gives negative charge, it will stick to the positive electrode. Okay, once the particle has been negatively charged, it is forced to the positively charged plate. Then the particles are removed from the plate by knocking action. Okay, that one is ESP. Now this is the diagram. I will update this in CN. So this is the wet scrubber, where you have gas with contaminants and have water sprinkler over here. So the water will absorb the pollutants and come into this chamber. So here water plus the pollutants. So clean gas come out from here. Now dry scrubber just now, where we use chemical agents to neutralize the acidity perhaps. Okay, it is not limited to chemical agent as well only. It has other types of media or other types of method. Okay, but the principle is dry scrubber, it use certain media inside here, different with the wet scrubber over here. Okay, for the ESP, okay, just now from the description, the gas is forced to have negative charge. Okay, it is forced to have negative charge so that the particles with negative charge will stick to this positive charge collector plates. Okay, here is, sorry, when you have negative, so it will come to the positively charged plate. Okay, they will accumulate over here on the positively charged plate. Then the pollutants will be collected by knocking. So they will knock or give some force to this plate so that the particles will fall down here, fall down to here, will be collected down here. Okay, so clean gas will exit the ESP. The efficiency of ESP is higher, even though the cost is quite high compared to the wet and dry, but the efficiency is higher compared to wet and dry. And it is low maintenance. Okay, any questions so far? Yeah. So these three is not the only method to treat the flue gas. There are more. Okay, you can read through journals and Google around what are the other methods. Perhaps you can use biofiltration where it involves the microbes. Okay. So another one is air filters. This one, for example, like air purifier. So the same concept used in the industry. They use air filters where the filtration media, it can be fabric or metal or ceramic. The purpose is to collect and remove dry particulates and contaminants, okay, such as dust, pollen, microbes, chemicals, everything. So these are the basic diagram of the air filter. I adapt from this website. This is a supplier for air filter for industry. Okay, so the filters, there are several types of air filters, inclusive HEPA, fabric, and cartridge dust collector. Okay, the air filter, it is limited to, like for example, very fine particles. If very fine particles in industry, perhaps they will use either the ESP or the wet scrubber, wet or dry scrubber. Okay, the air filters is quite limited and the efficiency in comparison with the scrubber quite low in comparison with the scrubber. Okay. Now, next is to quantify the emission. We have emission index, corrected concentration. Corrected concentration here, for example, in the first condition, your O2, you have, like for example, a certain ppm of O2 involved in your combustion chamber, a combustion process. But then the flue gases is diluted with at a certain extent of oxygen diluted so that it can meet the standard. Okay, then we will have emission factor. Now, emission index, this is the general equation where it involves mass of the pollutants. Okay, I here the species of the pollutants. F is the fuel use. Okay, so it's the ratio of the mass of species I to the mass of fuel burned. Okay, the specific equation will involve the mole fractions of the species and the gases, CO2, CO2 and CO, multiplied by molecular weight of the species and the fuel. Okay, the Y here is the mole fraction. X over here, okay, take note, this X is the number of moles of carbon in fuel. Okay, take note, X over here, mole of carbon in fuel, not in the pollutants. Okay, we go through example how to use the equation. This example is from fuel combustion engine. Then they measure on the exhaust products. These are the composition of the exhaust product. CO2, CO, O2, hexane, and O. Okay, the engine is fueled by isooctane. This is the fuel use, isooctane. What is the chemical formula? Isooctane. Octane, how many carbon? 8. H, 18. Octane. So it asks you to determine the EI, emission index, of the unburned hydrocarbons, expressed as hexane. Okay, so this one is the unburned hydrocarbon. So it asks you to determine the EI for this hexane. So using the equation, our species now, the pollutant is the hexane. Okay, using the equation from the composition measured over here, okay, we plug it into the equation where hexane is 367 ppm. Okay, this one comes from 367 ppm, part per million. Okay, so this one is the CO, 0.12%. Okay, and this one, this is CO. This comes from the CO2. X mole of the fuel. Okay, so 8. C of the fuel. Okay, that's why 8 over here. So multiply by molecular weight of the hexane, divide by molecular weight of the octane. Okay. From here, do the calculation, then you will get this figure of EI, emission index. Okay, the equation will be given. You just know how to use it, which info to plug in. Okay. Now then, here it shows it redo the calculation taking into account the unburned hydrocarbon together with the CO, CO2 down here. Okay, by including the unburned as one of the exhaust product over here, the emission index is not that big different. Okay. Now this one, we'll skip this one. Here. Let's say the question asks you to find whether the CO release is affecting the environment or not. Okay, how to know and how you can calculate the CO content. Now, for example, here we have ethane and air with 19% excess. Is supplied to a combustion chamber and produce these gases. This one I adapt from one of the example in chapter 2 or 3. Okay. Okay, here we have ethane plus the air, 19% excess. This question stated this is your flue gases. Okay. How do you know if the CO is affecting the environment or not? First thing, we need to generate the combustion equation first. Then after you generate the combustion equation, you will have the actual combustion equation. Okay. This one you try to do on your own. Here I will give you the final combustion equation. Okay, after you do all the calculation, you should be getting this combustion equation. Okay, let's say this is the final combustion equation. So here, our focus is on the CO. Okay, CO, this part. It asks you to analyze is the CO affecting the environment. How do we know? So 1 mole of ethane producing 0.18 moles. Okay. Now we know that from the EI just now, even though it is dimensionless, but you notice it is in weight unit, okay, kg or g. Now, after you identify how much mole of CO produced, try to find out what is the EI. What is the concentration of the CO produced? Okay, for example, that 1 kmol of C2H6, you will have 0.18 kmol of CO, right? Okay, so to convert it into weight unit, 1 kmol of C2H6 is equivalent to 30 kg C2H6. Okay, so from here, equivalent to CO, sorry, kg. So 1 kg of C2H6, you will have okay, 1 kg C2H6. How many kg CO that you will get? Zero point 0.16 kg CO, right? Huh? 168. Okay. Now, how to analyze? I'll share with you the API standard for Malaysia. Okay, this one, the API Malaysia guideline, the latest I can find is 2000. Okay, we focus on the table 3, the API values. Okay, another table is this. This one is the revision 2020. Okay, CO2. Only certain gases only. Okay, we follow the 2001. Now, table 3. From table 3 over here, let's say we just take the value over here, 0.168. Okay, let's say you just take this value. Zero 0.68. Okay, so refer to the table for the CO volumetric units. The lowest here in step 5, 0.45. Make it bigger. Okay, we focus on the CO volumetric unit. Okay, let's say you take the value just now, 0.168. Check for CO lesser than this. Okay, the minimum is 5 over here, step 5. So after we had conclude the step over here, first you find the CO value. Then you check the step. Okay. After you find out the step is below 5, then you refer to table 4, where it conclude whether the reading is good, moderate, or unhealthy. Okay, here the API step 0 to 50. So it is the status is good, the level of pollution low, and has no ill effects on health. Okay, so from the reading just now, the CO, let's say we just take that number 0.168. So the status of your CO release is good, still manageable. Okay, it has low effect on the health. Okay, pollution is low. Okay, let's say when you calculate, you find out your CO, for example, you find out your CO is, let's say, 35. The concentration, the ppm is 35. So this is the API step 350. Okay, the API step 350 refer to the table 350 falls under here. It is hazardous. The status is hazardous, severely affecting the health. Okay, that's how you conclude whether your flue gas is whether in good or hazardous or how. Okay, the level of pollution. Okay, let's say your CO reading falls under hazardous. So the next question might be, how can you reduce the CO concentration? What do you think? How can you reduce the CO concentration? Yes, convert the CO2, the water gas reaction, one of the method. Okay, or perhaps you can use the equipment that we discussed earlier, the scrubbers, okay, and perhaps other methods. Okay, so this is how you read the table. First, find out the concentration of the pollutants. This table shows you for CO, O3, SO2, and O2. Okay, then check the ppm, check the API stats. Once you get the API stats, you check the next table whether it is in good, moderate, or hazardous condition. Okay. This table will be provided if this kind of question is asked. Can how to read the table, how to conclude, and how to propose a method if it is in hazardous status. Yes. To the step. From this calculation, let's say we assume this is the ppm, because this one is kgco over kg fuel, right? Let's say we take this as the ppm. Directly take this as ppm. Then check the table over here. And the CO. Then check the steps. Okay. Okay, now I move to corrected concentration, where concentrations of the flue gases corrected to a particular level of O2 in the product stream. Because to remove the effect of various degree of dilution, so that it is a true comparison of emission level. So you will know the exact real value of your emission without the dilution factor. Okay, the corrected concentration, it can be expressed either in wet or dry basis. Now, the dry mole fraction and wet mole fraction we have gone through in the previous chapters, where you should find the N total of your product gases. Okay, the mole of CO2, H2O, O2, and 2. Okay, whatever gases produced, total up, you get the N total. That one, if H2O include, so that is wet. Okay, if without H2O, it is dry. Okay, this one is from previous chapters. Now from there, this one is a simplified version of the ratio and mix and over and dry. Okay. So this one, This is the one that I want to emphasize, where A over here is different from the A previously. In final exam, I conclude, how to say, I put this under subtopic, sorry, under corrected concentration equation. Okay, so that you are not confused with the A over here. Because in previous topics, A, we know A is the spot. This one, right? To count out the spot, the A spot, the A actual, we refer as A. But in corrected concentration, A over here is the oxygen coefficient. Okay. Now this is the equation for wet and dry. Derived from the ratio of mole fraction just now. Okay, derived from here. It derived from here. This A is this one. Okay. Now, from here, if you are required to find out the mole fraction of the species in dry, so you just directly use the equation where we know the N total wet and total dry. Yeah, I introduce the equation first, later we do the example. Okay, let's say, for example, it mentioned, it asks you to calculate 200 ppm NO corrected to 3% O2. 3% O2. Okay, so to correct a measured concentration or convert from one O2 level to another one. That means in this 200 ppm NO initially measured at O level 1, O2 level 1. Now it asks you to correct this concentration to 3% O2. So this one is O2 level 2 to the corrected concentration. Now this is the equation. The new concentration after corrected to certain percentage. Okay, this one is from the initial concentration before the correction. Okay. Where the N mixed wet comes from the previous equation. Okay, now we go through examples so that you understand how to use the equation. Using the previous data in example 1, the exhaust gas produced, it asks you to convert the given NO concentration to wet basis. In initial example, it is measured in dry basis. Okay, so to convert to dry basis, if you still remember, there is one example in previous chapter, measured O2 in dry basis, then you need to recalculate to wet basis, where you need to correct it back, right? So similar to that calculation, but here it directly gives you the equation. Okay, so mole fraction of dry. This is the new to find out. You include the wet and the N total ratio. Okay. Now, first, we calculate the ratio of total number of moles in a wet mixture to the number of moles in dry mixture. Using equation 3b. Okay, equation 3b, where you have the dry info. Your blue gases measured in dry. Now you want to find it in wet. Okay, so you need to find the A first. A for the dry. Sorry, A. Okay, so using the info of your exhaust gas in dry basis, plug in all the infos that you have, so you will get this A value. Okay, once you get the A value, plug in into the ratio. Equation 2, then you get this. Okay, why you need this? Because you need to use them in order to find the wet basis. You need to find this, the ratio, where this ratio calculation is involved and is related to the A. Okay, you need to find the A. Because you have A in this equation. So that's why you need to find the A in the first place. Okay, once you get the ratio, plug in the value, multiply with your initial concentration for dry basis. Then you get the NO concentration in wet basis. Okay. Again, I repeat, this is the main equation that you need to use to find the wet basis, where the dry basis concentration multiplied with the ratio of the total concentration, total mole. But this value, you don't have the value because you missed the A. The A is unknown. So you need to find the A first using the dry composition. Okay, so from there you can get the wet basis. This is another method. Otherwise, you can apply the step as in previous examples that you do the correction. Okay. Now this one, when you are required to do the correction from a certain concentration of O2 to 5% O2. Okay, in the previous exhaust product over here, it is mentioned the stream containing 2.3%. Okay, initially, it is measured O2 is 2.3%. Now, it asks you to correct the NO concentration to 5%. Okay, using equation 6b. 6b, because why we use 6b not 6a? Because the exhaust product is in dry, measured in dry basis. So that's why you use 6b. Now using 6b, plug in all the infos that you have. At the initial O2 concentration, 2.3, you'll get this. Okay, then find out the N mix at 5% O2, you'll get this. Okay, this is to find the N mix. the total mole of the gases at this O2 concentration, okay, 2.3 and 5. First level and second level. Then plug in into the main equation, which is this one. This is the one that you need to find. O2 at 5%. Okay, level 1 is your O2 at 2.3%. So plug in the inputs, the initial NO at 2.3%, which is the 76, multiplied by the N mix at initial concentration and N mix at second level concentration. Okay, so the ratio multiplied by the initial NO, you get the second level NO. 5% O2. Okay, so when the O2 concentration increase, the NO concentration reduce. Okay, at O2, 2.3%, NO is 76, but at 5%, reduced to 65. Okay, it is diluted. How to increase this 5%? Initial measured O2 is 2.3. So how can you increase to 5%? What do you think? How can you increase the 5% over here? Initially, it measured 2.3%. So the second level is 5%. How to increase this 2.3 to 5%? Where this 2.3 comes from at the first place? Huh? From the air supplied, yes. From a certain amount of air supplied, then you measure 2.3. So to increase 5%, increase the air input as well. How to increase? How much to increase? You have to do back calculation. Okay, that one is for your knowledge, Marina. I won't ask that kind of question. Okay. Now there are others emission measures. Okay, very specific emission, as I mentioned earlier. We can measure the emission based on the mass specific emission or emission factor. mass of pollutant divided by the fuel energy supply. Okay, here it involves the energy. For example, we have here fuel use is methane. Okay, it asks you to determine the emission factor, EF. Emission factor. For example, kg of CO2 released per gigajoule per energy produced. Complete combustion, okay, of methane at this condition. First thing, find out your combustion reaction in order for you to know how many moles of CO2 produced. Okay. Here it doesn't mention any excess air or anything. So assume at theoretical A start. Okay, so here is A start. And you don't have O2 in your flue gas. So now the combustion reaction, this is the combustion reaction with methane as the fuel. You have 1 mole of CO2 produced. Using the equation to find the emission factor, mass of pollutant. The pollutant over here, we focus on the CO2. Okay, mass of pollutant. Find out the mass of pollutant. 1 mole multiplied by the molecular weight. So you have this mass of pollutant. Then the fuel energy supply. Fuel energy supply. Fuel is your methane. Fuel is your methane. So methane, we want to find the energy. Energy here, it involves the LHB. Where you can get this LHB if it is not given. From table, here I already mentioned, table A27, or from the combustion equation. Reactant product, sorry, heat of product minus reactant, or reactant minus product. Okay, that one you can find out the LHB. Now the fuel energy supply over here is based on the LHB of the methane. Methane, 1 mole as well. Okay, so the LHB given multiplied by the molecular weight. So you will have here in terms of gigajoule, because here it mentioned per gigajoule. Okay, here LHB fuel multiplied by the molecular weight. Molecular weight here is just to convert to joule mole. Okay, joule over mole, kilojoule over k mole. If let's say the LHB is given is already in, let's say already in NJ k mole, so you don't need to multiply the molecular weight anymore. Okay. Now from here, mass of the CO2 is what? Over this. Okay, so you will get this amount of emission factor. Okay, so that's all for our last topic. We are done with all the topics. Okay, so we are done with all the topics. For the rest of the weeks, you can proceed with your group assignment. Again, to repeat, our test will be bring forward earlier to 11 a.m. For those coming late just now, we bring forward to 11 a.m. Due to that cell is not available at 12:30. Anyone have class at 11 a.m.? Bennett? Kenna? You have class? What time? 11. What class? Dr. Lai. I will request. I will request for you. Others? Not sure. Okay, so only Bennett. I will request Dr. Lai. Dr. Lai. Remember, 11 a.m. Please spread the words. Inform your friend. These are the topics covered. And remember, the test is 20%. Okay, there will be 2 questions. Question 1 involves CO3, which will involve a lot of calculations. CO4 is theory part, sustainable theory. Okay, what else? Again, for the group, today is the last date to register. Bennett, please register yourself in the group. I have assigned 5 groups over here. Group 1 and group 2 are the full. 3, 4, 4 and 5 stay 0. Okay, ask your friend to register by today. If not, assignment is 15%, if I'm not mistaken. Okay, anything else before we end the session? Any question?